Hi guys, so today we're going to review systems of inequalities. So until this point we've just been doing systems of equations. So now we're going to look at what these look like if we're talking about inequalities. So to start, we're going to review just how to actually graph an inequality. So if you remember with inequalities, there's going to be some shading. So we're going to start by actually graphing the line y equals negative 1/3 x plus 2. So this is going to have a y-intercept of 2 and a slope of negative 1/3. And then what I need to consider on my line. If I have a greater than or less than symbol and it does not have the or equal to, I'm going to use a dashed line instead of a solid line. If it's going to be an or equal to, then I will use a solid line. So in this case, since it's y is less than or equal to, I'm going to use a solid line here. Then the other thing we need for an inequality is shading. So if we have a less than symbol, we're going to shade below the line. And just kind of the way to remember that, the L pretty much looks like a less than symbol. So if it's a less than, we shade below the line. All right, so let's look at this next one. In order to graph this, I need to get y by itself. So negative y is greater than negative 2x plus 3. But in order to get y by itself, I need to multiply or divide by a negative 1. And if you remember, if you multiply or divide by a negative, that is going to change your inequality symbol. So instead of greater than, it is now less than. So now this is 2x minus 3. So 2x minus 3, I'm going to have a slope up 2 over 1. And this time, since it's less than, since it's less than and not or equal to, I'm going to use that dashed line. And then again, this one is also less than, so I'm going to shade below this line. Now, when you're trying to figure out if it's above or below, look at your y values in relation to the y-intercept, okay? We're shading the y's that are below the y-intercept. So now what we're going to do is we're going to look at a system of inequalities. And all this is going to be is this is going to have multiple shaded parts. Our solution is going to be where all of the shading meets up. So let's go ahead and graph just our lines to start. So the first one here, y is greater than negative 2x minus 5. So y-intercept of negative 5, slope of negative 2. Since its y is greater than, it's going to be a dotted line. And I'm going to hold off on the shading for now. All right, so now let's do our second line. Our second line, y is less than or equal to x plus 3, y-intercept of 3, slope of 1, solid line. All right, then the next one, y is greater than or equal to x minus 2, y-intercept of negative 2. And then this one is also or equal to, so we're also going to use that solid line. So now I need to look at my shading. Okay, so shading on this blue graph, if we look at that, it's going to be y is greater than the blue line. So above the blue line. For the green line, I'm shading below. And then for the purple line, I'm shading greater than or equal to, so I'm shading above. Now, it's kind of a big mess right now, but if you can look and see, there is an area where there are all three colors. So what I'm going to do is I'm going to go ahead and erase, so this is a little bit clearer to see. So that part that was above the purple, below the green, and above the blue is this region in here. So that region will be my solution. So it also asks for us to give one point that is a solution and one point that is not a solution. So what's different about this than regular systems, we don't just have one answer. Any answer that falls within that shaded region, which we also call our feasible region, any answer that falls in there is a solution to that system. So there's multiple correct answers here. So one example, 0, 0 is a solution. 1, 3 is a solution. Something that is not a solution, something outside that region. So like 2, negative 1 is not a solution to that system. Now what we also need to consider is the solid lines and dotted lines. If a point falls in that out on the boundary of that shaded region on the solid line, it is still a solution. But if it falls in the boundary of that shaded region on a dotted line, it is not a solution. So the dotted line is not a solution because it doesn't actually make that first statement true. All right, so let's look at the next one. Let's go ahead and get y by itself in that first equation. So 3y is less than negative 2x plus 6. So y is less than negative 2/3 x plus 2. So I'm going to go ahead and graph this one. So y-intercept of 2, slope of negative 2/3. It's dotted line because it's not or equal to. I'm going to hold off on the shading again. Let's do the second one. Y is greater than or equal to negative 2/3 x plus 4. So y-intercept of 4, slope of negative 2/3. All right, and then I'm going to go ahead and graph this last one, or the third one. Let's get y by itself. So y is less than 2x minus 2. And again, this one would be a dotted line. And then the last one, x is less than 4. So that's going to be a vertical dotted line at 4. All right, so now let's consider our shading. I want to shade left of 4. I want to shade above the green line. I'm sorry, below the green line. I want to shade above the purple, and I want to shade below the blue. Well, let's just look at just those two. Let's look at just the purple and the blue. If I shade where y is greater than or equal to that purple line, and where y is less than or equal to that blue line, is there anywhere that the blue and purple meet up? So since those 2 points never meet up, the other equations don't even matter at this point. This graph actually has no solution because there is not a place where all of the shading is ever going to meet up because the blue and the purple will never be both shaded in the same spot. All right, so now let's work backwards. So now what we're going to do is we are going to write the system from the graph. So I'm just going to start with one equation at a time. So I'm going to start with this equation here. So that's a vertical line when x is negative 3. So that's going to be x and negative 3. So now I just need my symbol. Since it's solid, it's going to be or equal to. Since I shaded right, I've shaded all the values that are greater than negative 3. So that's my first equation. My second equation, I'll use this one here. So that line has a slope of 1/2 and a y-intercept of negative 2. It's a dotted line, and I've shaded above it. So that's going to be y is greater than 1/2 x minus 2. And then my last one, that is a dotted line. The slope is negative 1/2. The y-intercept is 1. And I have shaded below that line. So that is the system of inequalities that shows that shaded region. All right, let's go ahead and try this last one here. I'll start with the solid line. That has a slope of negative 1, a y-intercept of 2, and I have shaded above the solid line. So that's the purple equation. Then we go to this one over here. That has a slope of 3x, a y-intercept of 2, and I have shaded below that line. So I would say y is less than 3x plus 2. Then last one, that has a slope of negative 1, a y-intercept of 2. Oops, sorry about that. That's the line we already did. Let me go ahead and do this last one over there. All right, so that one has a slope of 1/3, a y-intercept of negative 1, and I have shaded above that line. So y is greater than. Again, it's not equal to when it's a dotted line. All right, so the last thing we're going to look at is just a word problem, just an example of some of these applications here. We're going to do a lot more of this on Monday when we get to linear programming. So you have $60 to spend on toys. Stuffed animals cost $3. Cars cost $2. You want to buy more cars than stuffed animals, and you want to buy a minimum of 4 stuffed animals. So what's very important on these is that you define your variables, very similar to what you did with the word problems with systems. So the two things I'm looking for here, I want to see how many stuffed animals I can buy, and I want to look at how many cars I could buy. So the equations that I have here, we'll start with the simple ones. I want to buy more cars than stuffed animals. That means that cars has to be greater than stuffed animals. The other information it tells me is that I want to buy a minimum of 4 stuffed animals. So that means that stuffed animals has to be at least 4. Then the other equation has to do with the cost. So I have $60 to spend. So I cannot spend more than $60. What's making up that cost? Stuffed animals cost $3 and cars cost $2. So then if I want to actually graph this, I'm going to go ahead and solve for y. So I get that y is less than or equal to negative 3 over 2x plus 30. All right, I'm going to go ahead and rewrite that though over here. All right, so now let's go ahead and actually graph these values. So I'm going to go ahead and label this by 2. So 2, 4, 6, 8. And then 30 will be 1 off the graph. So I'm going to start by graphing that negative 3 halves x plus 30. So from 30, I'll go down 3 over 2, down 3 over 2, down 3 over 2. It is a solid line, and I'm going to wait on the shading until the end. All right, go ahead and graph the blue line. Y is greater than x. And again, let me go ahead and label this the same way. All right, so y is greater than x, just as a slope of 1, but this one actually is just a dotted line because it's not or equal to. Then the last one on there, y is greater than or equal to 4. That is a solid line right here. So now let's look at our shading. I want to shade to the right of the purple, above the blue, and below the green. So where all 3 of those would meet up would be in this triangle right here. So the reason we like the graphs of this is because that shows us all of the possible situations instead of having to list all of those possible points. So now it says give 3 examples of solutions. Well, remember x was our animals, y is the cars. So there's a lot of different possibilities here. For example, 4, 8. So 4 animals and 8 cars, for example, would be a solution because it does fall on a solid line. Another example to this system could be 8 and 12. So 8 animals and 12 cars is also a solution. All right, and then again, anything that falls either in that shaded region or on the solid line would all be possibilities. So next one's asking if you'd be able to buy 9 cars and 12 stuffed animals. Keep in mind the cars is the y, the stuffed animals is the x. So if I go to an x of 12 and a y of 9, that is outside that shaded region, so no, that is not a possibility. All right, so we're going to do a lot more with word problems on Monday when we get to linear programming, but this is a pretty good introduction and just a little bit of a review for systems of inequalities.